Okay, we're still in 10.1 of Barnett, and having learned some of the limit properties, why don't we take a look at some examples using those. So here's one example here. We have the limit as x approaches 2 of x squared minus 3x. So we're taking the limit of this function. Well, recognize that this function is the difference of two other functions, namely x squared and 3x. So we could rewrite this limit as the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 3x, using the difference property, which was property 4 on the previous slides. Now, before we get to how we obtain this answer here, let's break this down into further detail. The limit as x approaches 2 of x squared could be further broken down by the product property as the limit as x approaches 2 of x times the limit as x approaches 2 of x, right? Because x squared is the same as the product x times x. So that gives us this first limit here. Now for the second limit, we have a constant times a function, 3 times x. So we could write this as minus 3 times the limit as x approaches 2 of just x, using the constant times function property, right? This was property 5. Okay, so with that in mind, let's see, what could we do next? The limit as x approaches 2 of x is just 2. The limit as x approaches 2 of x is just 2, minus 3 times the limit as x approaches 2 of x is 2. Right? Remember, that was property number 2. The limit as x approaches c of x is just c. c in this case is 2. So we end up with 4 minus 6, or negative 2. That's how we got that answer here. 4 minus 6, or negative 2. However, notice that had we started this problem over, right here, limit as x approaches 2 of x squared minus 3x, if we had just plugged in 2 for x in order to evaluate the limit, we would have gotten the same answer right away. 4 minus 6, or negative 2. Keep that in mind as we look at example 2. We'll come back to this thought. In example 2, we have a quotient, so we use the quotient rule. The limit as x approaches 4 of this quotient can be rewritten as the quotient of the limits, 2x and 3x plus 1. Again, we could have been more specific here and turned this into twice the limit as x approaches 4 of x. And we could have turned this into the limit, 3 times the limit as x approaches 4 of x plus the limit as x approaches 4 of 1. And what would we have obtained? We would have obtained 2 times 4, which is 8. And at the bottom, we would have obtained 3 times 4 plus 1, which is 13. And that's how we get 8 over 13. But, once again, notice that if I had started this problem over right off the bat, had I plugged in 4 for x, I would have gotten the same answer. So here's what I mean. Evaluate the limit by plugging in x equals to 4, and we get 8 over 13. We get the same answer. So from these examples, and your book goes into a little more explanation, I highly recommend you read that, we can conclude that in general it is true that if f is a polynomial function, like in example 1, x squared minus 3x is a polynomial, then the limit as x approaches c of f of x is simply what you get when you plug in c into your polynomial. So you can evaluate limits for polynomial functions by plugging in c for x. Likewise, if you have rational functions, as long as the denominator is non-zero, when x is equal to c, you can evaluate the limit by plugging in, just like I did here. So instead of going through the limit properties, you could right away plug in 4, because 4 doesn't give you a zero denominator, and that's why you're okay. That is a very important fact that will really make your life easier. You don't have to go through all the properties when you have polynomial and rational functions. You could simply plug in. Okay, so with that in mind, let's move on to another topic here, indeterminate forms. It is important to know that there are restrictions on some of the limit properties. In particular, if the limit as x approaches c of r of x is 0, then finding the limit as x approaches c of f of x over r of x, some quotient that has r of x in the denominator, well, that may present difficulties, since the denominator is now 0, right? You could see this again using the quotient property. this guy would be equivalent to saying the limit as x approaches c of f of x divided by the limit as x approaches c of r of x. And we're saying that the bottom one is 0, right? So you would be dividing by 0. Well, if it just so happens that the limit as x approaches c of the top, f of x, is 0, and the limit as x approaches 0 of some g of x, the bottom here, is 0, then the limit of that quotient, f over g, is what we call to be indeterminate. Okay, when we get a 0 over 0 limit, we say that it's indeterminate. The term indeterminate is used because the limit may or may not exist, so we have to be careful there. Here's an example. This example, in fact, illustrates some techniques that can be useful for indeterminate forms. If you look at this limit, the limit as x approaches 2 of x squared minus 4 over x minus 2, that's a rational function. And notice plugging in 2 gives us 2 squared, which is 4, minus 4, a 0 on top, and 2 minus 2, a 0 on the bottom. So we get indeterminate form. So what you want to do in that case is use algebraic manipulation to simplify the quotient as much as you can. So in this case, we factored x squared minus 4 into x plus 2 times x minus 2, and that allowed us to cancel out a common term, x minus 2. Doing that turns the original quotient into this polynomial, x plus 2, which you can now solve the limit of by plugging in 2, and you get 4. So algebraic manipulation or simplification here is often useful when the numerator and denominator are both approaching 0. So that's one technique that you could use. Why don't we look at some examples next? Okay, so this is something called the difference quotient, which will come into huge play a little bit later on in this chapter. But for now, let's think of it as just finding the limit problem. So let f of x equal 3x minus 1. Find the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, let's break this down. Let's break each one of these pieces down. If f of x is 3x minus 1, what's f of a plus h? Well, think of it this way. Every time you see x, you're going to write a plus h instead. So you will get 3 times a plus h minus 1, or 3a plus 3h minus 1. What is f of a? Well, again, if f of x is 3x minus 1, every time you see a, just write, every time you see x, just write a. So, with that in mind, here's what we get. The limit as h approaches 0 of f of a plus h minus f of a all over h is going to be equal to 3a plus 3h minus 1. Oops, and I'm really sorry. Make sure you don't make the mistake I just made. Don't forget to write the limit as h approaches 0. When you're calculating limits, you have to carry the limit as h approaches 0 along for the ride until the actual point in the process where you evaluate the limit. So make sure you have limit as h approaches 0. Now we can substitute for f of a plus h by writing 3a plus 3h minus 1, right? And f of a, we said, is just 3a minus 1. So minus 3a minus 1 all over h. Okay, well, let's keep going here. Let's keep simplifying this as much as we can. Notice that this is 3a plus 3h minus 1 minus 3a, when you open up the parentheses, plus 1 all over h. And the minus 1 and the plus 1 will cancel, and the 3a and the negative 3a will cancel. So that gives me the limit as h approaches 0. Notice I'm still writing the limit all along of 3h over h. That's all that's left. Notice I can cancel the h's here, and that gives me something that I can evaluate. So here I'm not going to write limit anymore because I'm just going to evaluate this. The limit of a constant is a constant. So I get the answer 3. Here are the steps one more time. You could pause the video here just to make sure you understand each step. But that's how we get the answer 3. And I want to leave you with a summary of what we did. We started by using a table to investigate the idea of a limit. This was an intuitive way to approach limits. Then we solved the left and right limits at a point where the same. The limit at that point existed and it was equal to those. We saw that we could add, subtract, multiply, and divide limits. And we now have some very powerful tools for dealing with limits that can go on to our study of calculus.